Something extraordinary has just happened in our solar system, something with consequences that scientists are still struggling to comprehend. For the first time in recorded history, an interstellar object appears to have violently disintegrated as it passed through the inner solar system, and the implications have rippled across every observatory on Earth. Its name was 3I/ATLAS, humanity's third confirmed visitor from another star system, and according to Harvard astrophysicist Avi Loeb, the object did not merely brighten or fracture. It underwent catastrophic collapse, not a gentle shedding, not a typical cometary breakup, but an explosive event so extreme that millions of fragments may now be dispersing through space like shrapnel from a cosmic detonation. The shockwave through the scientific community was immediate. For months, astronomers had been monitoring strange behavior, sudden increases in brightness, unusual coloration, and mass loss rates that defied the physics governing known comets. But no one expected this ending. The calculations released just hours ago suggest that the object's structural integrity collapsed under forces it was never meant to withstand. According to Loeb, the sheer scale of material expelled implies that the original nucleus could not have been the small, icy body Hubble imaged in July. Something far bigger must have been hiding beneath the surface. Something that simply could not remain intact as it approached the sun's blistering radiation. And yet, for all the drama of the natural explanation, another possibility now stands alongside it. One Loeb himself has stated deserves consideration. What if the explosion was not entirely natural? What if something inside 3I/ATLAS malfunctioned, ignited, or activated under conditions it was not designed to experience? What if the object was never fully inert to begin with? As observatories scramble to capture the final traces of debris before they disperse beyond detection, one question grows louder than the rest. Did we just witness the first natural destruction of an interstellar comet, or the catastrophic failure of something engineered? The window to answer that question is closing fast. When 3I/ATLAS was first discovered on July 1st, 2025, astronomers treated it the way they treated its predecessors. Oumuamua in 2017 and 2I/Borisov in 2019. At first glance, it looked like another icy wanderer from the galactic neighborhood, a relic tossed between the stars for millions or even billions of years until gravity finally brought it into our solar system. Its faint glow, slow rotation, and chemical signatures suggested nothing out of the ordinary. For most of July, nothing about the object seemed remarkable at all. But interstellar visitors have a habit of defying expectations. Oumuamua had no visible tail, yet accelerated as if pushed by unseen forces. Borisov behaved like a perfectly normal comet, shattering no models but confirming that interstellar objects could be natural and unremarkable. 3I/ATLAS appeared poised to take a place between these two extremes. Comet-like in composition, but modest in behavior. No alarms, no theories. Just another fragment from a distant star system drifting through our neighborhood. Observatories worldwide integrated the object into their observational schedules. Hubble captured early images. The James Webb Space Telescope scheduled infrared passes. Ground-based observatories in Hawaii, Chile, and Spain prepared spectroscopic campaigns. The scientific community saw 3I/ATLAS as a valuable but predictable visitor, one that would help refine models of interstellar composition, but not challenge fundamental assumptions. That confidence lasted barely 3 weeks. By late July, Hubble's high-resolution imaging revealed something unexpected. The nucleus was extremely small, only 1 to 2 kilometers across. Meanwhile, early spectroscopic readings hinted at a volatile mixture of ices that should not survive long near the sun. But those anomalies were little more than curiosities until the brightness changes began, until the acceleration started, until the mass loss rates broke every chart. Only then did scientists begin to revisit their assumptions. Only then did the global network of observatories start looking at 3I/ATLAS, not as a passive traveler, but as something deeply unstable, something behaving in ways no comet ever had. No one expected the story to end with an explosion, but in hindsight, the warnings were there from the very beginning. The first major red flag came from a simple question: how much mass was this thing losing, and how fast? As 3I/ATLAS drew closer to the sun throughout August and September, its rate of sublimation, material evaporating into space, began to surge. At first, it expelled around 330 kilograms of gas and dust per second. That's high, but not unheard of for a comet under solar heating. What followed, however, pushed the boundaries of natural physics to their breaking point. By perihelion on October 29th, 3I/ATLAS was losing material at a staggering 2 million kilograms per second. That meant that every second, the object was ejecting the mass equivalent of 20 fully loaded cargo jets. Over the course of a day, it was shedding more than 200 million tons of material, an amount no known 1 or 2 kilometer comet could physically contain. According to Loeb's calculations, this level of mass loss required a surface area of at least 617 square miles. In other words, a sphere around 14 to 20 kilometers in diameter. But Hubble had already proven the nucleus was tiny. There was no way around it. The numbers didn't match. Either the observations were wrong, which seemed unlikely across multiple independent telescopes, or the object was presenting vastly more surface area than a single intact body ever could, and that led Loeb to the only natural explanation left: fragmentation, catastrophic fragmentation. If 3I/ATLAS had shattered into countless smaller pieces before or during perihelion, then each fragment would contribute its own sublimation surface millions of surfaces. Millions of microjets of gas escaping into space. Together, they could produce the massive energy output observed in October. But that explanation introduced a new question. If the object fragmented, why did telescopes fail to observe a standard debris cloud? Why was the brightness increase so concentrated and organized? Why did 3I/ATLAS behave not like dust dispersing from a shattered rock, but like something undergoing a coordinated, structured transformation? The math demanded fragmentation. The imagery did not support chaos. Something didn't add up. As early as October, astronomers monitoring 3I/ATLAS noticed a stunning trend. Its color was changing. The object was becoming bluer, not slightly bluer, not tinted or nuanced, but unmistakably and dramatically shifted toward higher energy wavelengths. The phenomenon was so extreme that Loeb described the object as bluer than the sun during peak brightness. That alone should have triggered widespread alarm. Comets do not turn blue, not ever. Standard cometary behavior produces a yellowish or reddish hue due to sunlight scattering off tiny dust grains. Dust makes objects red. Gas emissions can cause greenish tints depending on molecular composition. But nothing in the catalog of known cometary physics produces a deepening blue flux during increased heating. The only natural mechanism that might produce such a spectrum is ionization of metallic compounds, something comets simply do not contain in surface-dominant quantities. The brightness spike made the anomaly even more troubling. As 3I/ATLAS approached the sun, instead of presenting the golden white glow of dust production, it flashed brighter in a polished metallic way, like a reflective surface catching firelight. Imagine a snowball tossed toward a furnace, becoming shinier, harder, more metallic as it melts. Nature does not do that. Chemistry does not do that. Some theorists propose that the blue color came from fine ice grains reflecting sunlight, but the spectral patterns didn't match. Others suggested unusually high carbon monoxide output. Again, the data disagreed. The shift was too steep, too clean, too rapid, and then an alarming possibility emerged. If the surface was turning metallic, was it because the icy outer layer had sublimated away, exposing something beneath? The blue shift became the first public crack in the natural comet hypothesis. And by the time the jets appeared, even the cautious scientists had begun to whisper the unthinkable. The next clue in the unraveling mystery came from fragmentation models. If 3I/ATLAS had indeed blown itself apart, then its physical structure would have undergone a radical transformation. Instead of a single nucleus with a smooth sublimation surface, it would behave like a cloud of debris, each fragment contributing its own outgassing jet, each piece carrying its own momentum as it accelerated away from the sun. Loeb calculated that the total surface area required to support the observed mass loss rates could only be achieved if the object had splintered into millions of fragments, not dozens, not thousands, millions. That level of fragmentation would turn the comet into a disintegrating swarm, a cloud of icy shrapnel stretching across tens of thousands of kilometers. Yet when the British Astronomical Association captured images on November 9th, the debris did not behave like debris. There was no chaotic haze, no messy explosion remnants. Instead, they captured something that made even skeptical astronomers sit up in their chairs. Organized jets, highly structured, directional, and astonishingly consistent. One anti-tail stretched nearly 1 million kilometers toward the sun, a direct violation of solar wind behavior. The primary tail extended almost 3 million kilometers in the opposite direction. Additional jets appeared in symmetrical patterns, forming linear plumes as if guided by internal channels rather than randomly venting gas. This was not the signature of debris drifting from a shattered rock. This was geometry. Natural fragmentation produces radial scatter. This event produced organized architecture. Each jet held a coherent direction over time, maintaining shape and orientation instead of dissipating. If the object had truly blown itself apart, the fragments were behaving with unnatural coordination. Loeb's team considered everything: rotation patterns, temperature gradients, fragment clustering. None of it could account for the organized structures through standard cometary physics. And so, reluctantly, one more hypothesis came into the spotlight: propulsion. The November 9th images changed everything. What astronomers expected to see was a standard dust coma, a diffuse, hazy cloud surrounding a broken nucleus, gradually dispersing under solar wind pressure. Instead, they found themselves staring at filament-like structures so geometrically precise that the first question circulating among research teams was whether the images were artifacts or camera glitches. They weren't. Independent observatories confirmed the same patterns. The anti-tail alone was unprecedented. Anti-tails occur when sunlight reflects off dust particles distributed along the comet's orbital plane. But 3I/ATLAS's anti-tail was almost 1 million kilometers long, narrow, symmetrical, and entirely backward, pointing directly toward the sun. Solar wind should push dust away from the sun, not allow it to stream backward. This was like watching smoke flow toward a bonfire instead of away from it. The main tail was even stranger, stretching nearly 3 million kilometers outward in a straight, unwavering plume. Not wide, not dispersed, razor thin. Maintaining that shape requires a stable, continuous emission source, something no fragmented comet can produce. Comet fragments spin chaotically, vent gas sporadically, and release dust in bursts. Their jets wobble, angle off axis, and collapse quickly. Not one natural process could generate geometric columns spanning millions of kilometers with that level of structural integrity. Then came the side jets, at least 7 distinct plumes angled with almost mathematical precision. They didn't flare randomly. They didn't break apart. They held orientation for hours at a time, suggesting a stable internal structure beneath the apparent fragmentation. These side jets were evenly spaced, forming an almost radial pattern reminiscent of a thruster array. Across every model, scientists found themselves stuck. If the nucleus was intact enough to anchor jets, then fragmentation must be limited. If fragmentation was as extensive as mass loss rates suggested, then coordinated jets shouldn't exist. The jets were too straight, too uniform, too persistent. Every attempt to simulate the observed geometry failed. Natural sublimation couldn't account for the stability. Fragmented debris could not form linear collimated jets, and solar wind dynamics actively opposed the anti-tail's direction. With each new image, the behavior of 3I/ATLAS looked less like a comet in distress and more like a system of controlled exhaust plumes releasing material with purpose. Some scientists suggested an exotic natural explanation: magnetic field interactions, electrostatic charging, or plasma instabilities. But all such theories collapsed under scrutiny. The jets were simply too ordered. And that forced researchers to consider a hypothesis that, under normal circumstances, would never be welcome in a peer-reviewed environment: artificial propulsion. Not because scientists wanted that to be true, but because standard physics could not reproduce what the telescopes were showing. The geometric jets became the tipping point. They were the feature that shattered the wall, separating acceptable scientific speculation from forbidden questions. This was not chaos. This was architecture. And if that was the case, then the explosion that followed might not have been an accident. In scientific circles, suggesting an extraterrestrial propulsion system is career suicide, unless the data leaves no other choice. Loeb is known for his willingness to consider technological explanations, but even he approached the possibility with restraint. His proposal wasn't a declaration, but a comparison. Based on exhaust pattern, energy distribution, and jet geometry, the behavior of 3I/ATLAS matched engineered propulsion more closely than natural sublimation. Artificial propulsion systems, ion drives, plasma thrusters, magnetohydrodynamic engines, produce narrow, high-velocity plumes. These plumes remain coherent, straight, and directional, even when subjected to environmental forces natural jets never do. That was the first red flag. The second was the exhaust velocity implied by the observed acceleration. For the object to gain speed beyond 150,000 miles per hour while losing mass at the recorded rate, the exhaust must have been expelled at far higher velocities than sublimated gas can achieve. In engineering terms, sublimation produces soft exhaust, low-speed vapor escaping from surface ice. But the jets of 3 I/ATLAS produced thrust-like forces powerful enough to alter trajectory. The math aligned more closely with engineered nozzles than with fractured ice. Another point in the propulsion hypothesis came from rotational behavior. Early in its approach, 3 I/ATLAS spun slowly and consistently. Yet after perihelion, when the jets intensified, its rotation began fluctuating in harmonic cycles. These fluctuations weren't random. They repeated at regular intervals, suggesting timed bursts or controlled power cycles, as if the object was reorienting itself through deliberate pulses. Thermal modeling added more evidence. The jets emitted heat signatures that didn't match pure ice vapor. Instead, they resembled plasma emissions, or ionized material undergoing acceleration. And during several observations, the object cooled abruptly after rapid brightening, another characteristic of controlled systems shutting down after a burst of output. But perhaps the most compelling argument for artificial propulsion is the problem of sustained acceleration. Objects passing close to the sun receive gravitational and thermal influence, but they do not accelerate after perihelion. They decelerate as they climb back out of the gravitational well. Yet 3 I/ATLAS gained speed steadily, measurably, undeniably, even as it moved away from the sun's influence. This is not how nature works. The propulsion hypothesis is not rooted in fantasy. It's rooted in math, spectroscopy, trajectory analysis, and physical laws. If natural physics cannot explain mass, heat, thrust, geometry, or rotation, then something else must. And that leads to a terrifying idea. Perhaps the explosion was not caused by thermal stress. Perhaps it resulted from a catastrophic failure of internal machinery. If 3 I/ATLAS carried something inside, fuel systems, volatile chambers, structural components, perihelion could have triggered instability. The object may have ignited, ruptured, or even self-destructed under conditions it wasn't built to endure. Alternatively, the breakup could have been intentional, part of a design dispersal mechanism, shedding outer layers or releasing smaller components into the solar system. For now, the propulsion hypothesis remains controversial, but every scrap of data, every spectrum, every jet analysis brings it closer to center stage. And as the acceleration data poured in, even skeptics were forced to reconsider. Acceleration is the part of the story that keeps mission planners awake at night because it violates the one rule our solar system has always followed. Objects obey gravity. They fall inward toward the sun, swing through perihelion, then slow as they climb away. But 3 I/ATLAS broke that rule. At perihelion, it was already traveling at more than 150,000 miles per hour, normal for a comet whipping around the sun. Yet after passing perihelion, its speed didn't level off. It didn't decline. It increased. The object accelerated at roughly 94 kilometers per day squared, a figure that made no sense under any natural model. Solar radiation pressure can nudge small particles, but not kilometer-scale cometary fragments outgassing can add minor thrust, but not at velocities exceeding engineered spacecraft. Comparison with Oumuamua provided an eerie precedent. Oumuamua also accelerated unnaturally, though far more subtly. At the time, astronomers attributed the change to outgassing. Even though no gas was detected, Loeb argued it might have been a light sail, a technological structure pushed by sunlight. Most dismissed the idea. But now, faced with an object whose acceleration dwarfed Oumuamua's, the community could no longer hide behind comfortable explanations. Then came the envelope anomaly. JWST detected a carbon dioxide cloud around 3 I/ATLAS stretching 348,000 kilometers, an absurd distance for a body smaller than Manhattan. That CO2 envelope would require either an enormous nucleus or impossible outgassing efficiency. Neither matched reality. Spectroscopy from Webb and Hubble revealed more inconsistencies. The iron-to-nickel ratios were wrong for natural comets. They were inverted in ways no known stellar nursery produces. The molecular passport of the object had all the right elements, but in the wrong order, like forged credentials. None of it added up. Natural comets have predictable behaviors: composition, gas release, energy absorption. 3 I/ATLAS violated every chart. every formula, every expectation, and the acceleration was the final straw. The object was moving like something with an engine. As November turned to December, astronomers tracked its trajectory with increasing anxiety. The acceleration wasn't chaotic. It followed a smooth curve, as if the object was adjusting course rather than drifting randomly. While the explosion removed the nucleus, the fragments continued along trajectories that indicated initial thrust. Acceleration after fragmentation, acceleration inconsistent with solar physics, acceleration without tail behavior matching natural sublimation. Whatever 3I/ATLAS was, it behaved like something that wanted to leave the solar system faster than it arrived. And as it sped away, the observational window began to close. By late November, scientists knew they were running out of time. The fragments of 3I/ATLAS, whether natural debris or engineered components, were dispersing rapidly. The closest Earth approach was scheduled for December 19, 2025, and every observatory capable of tracking the object prepared for what would become the most concentrated astronomical campaign in decades. Hubble, Webb, Subaru, VLT, Keck, Gemini, all of them dedicated time, even pushing aside deep space programs to prioritize 3I/ATLAS. This was the last chance to capture definitive data. Once January 2026 arrived, the fragments would fade beyond detection range entirely. No future telescope, however advanced, would ever be able to reconstruct the nucleus. The window humanity had been given was finite, fragile, and final. Every second of observation mattered. Teams across the globe worked around the clock. Spectroscopy teams sought chemical signatures in the debris. Infrared arrays mapped heat patterns. Radar networks attempted to capture fragment density. But the closer scientists looked, the stranger the object appeared. Some fragments behaved like typical cometary shards, dispersing under solar wind influence. Others maintained rigid trajectories, traveling in narrow formations without drifting. Several emitted faint but steady energy pulses, regular, repeating, synchronized, suggesting internal structure. This behavior divided the scientific community. Some insisted these anomalies were artifacts of imaging. Others argued that the fragments might still be venting gas in coordinated ways, but more and more researchers whispered the same fear. The fragments were not uniform. Some looked natural, others didn't. A few fragments spun with unnatural stability. Others maintained albedo levels too consistent for irregular ice. Some even exhibited reflective flashes at synchronized intervals, as if rotating panels were catching sunlight. And then there was the matter of mass distribution. Models predicted the fragments should form a cone-shaped dispersal. Instead, the fragments distributed themselves in clusters, tight clusters, drifting in parallel. If the nucleus truly exploded, why were some pieces behaving as if guided? Scientists fought over interpretations. Telescopes strained to gather more data. Every hour, the fragments grew fainter, smaller, more distant. Humanity watched 3I/ATLAS slip away, piece by piece, like embers blown across a dark sea. This was the last time Earth would ever observe it. The disintegration of 3I/ATLAS marks a turning point in how humanity understands interstellar objects, and possibly its place in the cosmos. For decades, the assumption was that interstellar visitors were inert relics, harmless wanderers that posed no threat and carried no message. Oumuamua challenged that. 2I/Borisov restored comfort, but 3I/Atlas shattered more than itself. It shattered complacency. If the breakup was natural, then it represents a phenomenon never before observed: the catastrophic collapse of an interstellar nucleus under solar stress. This would require new physics to explain mass loss rates, spectral anomalies, and geometric jets. It implies that interstellar space may contain objects with properties unlike anything formed in our solar system, new categories of cometary bodies, new models of thermal stress, new understandings of chemical formation. But if the breakup was artificial, or partly artificial, then the implications are far more profound. It might suggest that interstellar space contains engineered objects, that our solar system is being transited by constructs not built by humanity, that some objects are probes, vessels, machines, or fragments of something once greater. If 3I/ATLAS carried propulsion systems, structural components, or engineered layers, then its explosion could represent mechanical failure or activation. or disposal. Perhaps most chilling is the timing. 3 I/ATLAS arrived precisely when Earth possessed the exact combination of telescopes, sensors, and computational power needed to detect its anomalies. Had it passed by 50 years earlier, we would have recorded nothing more than a dim streak across the sky. The coincidence is staggering. Then there is the pattern. First, Oumuamua, then Borisov. Now 3 I/ATLAS. 3 interstellar visitors in 8 years, after millennia of silence. If this is random, it defies probability. If it is not random, then something out there is moving through the galaxy, regularly, intentionally, observably. As its fragments drift into the galactic void, scientists face a haunting uncertainty. Did humanity just witness a natural relic die? Or did we watch a machine malfunction? Or worse, did we watch one activate and shed its outer shell? Whatever the truth, 3 I/ATLAS has delivered a message. The darkness between stars is not empty. It contains objects capable of surprising us, terrifying us, and forcing us to reconsider everything we thought we understood. And as Earth loses sight of the fragments forever, one question echoes louder than all others. Was this the end of 3 I/ATLAS, or the beginning of something we have yet to understand?